Hello, my name is Bruce Krayenhoff, and today we'll be looking at a very interesting reinforcement learning paper called Diversity is All You Need, How to Learn Skills Without a Reward Function. So first, a quick summary of what the paper is about. We train multiple skills at once. We train them to produce discriminable states, which means that we have to train a discriminator alongside training the multiple skills. And we also encourage each skill to have high entropy. So if the skills are high entropy and we want to keep them discriminable, that pushes them apart so you get an actual diversity of skills. So first of all, let's have a look at what was produced. Where is that? All right. So here's the half cheetah. So you can see one of the skills that actually learned to run forward. It learned to do this funny thing. Tries to plow into the ground and go forward slowly. It learned to run backwards. And it learned all of these skills just to make the states discriminable from each other while still having high entropy policies. So pretty darn cool, eh? Learned to do flips too. Cool. So the paper, it's by Google Brain people and Berkeley people mostly, and somebody from Carnegie Mellon. And Sergey Levine's one of the people, a name you may recognize in reinforcement learning. So, cool. So, again, as we've discussed, they use discriminability as an objective. But to make them diverse, not just distinguishable, they learn skills that are as random as possible. That's maximizing the entropy as well. So that's how they push the skills away from each other. So the skills together will kind of cover the space of generating all possible states, basically. So here's the algorithm. So first of all, let's assume we're in the episodic case. We sample a skill, Z, from the uniform distribution. And then, so that skill really corresponds to a policy, right? So then you sample actions based on that policy. So that's your skill. And so the actions give you a new, then the environment gives you a new state based on that action. And then you also train a discriminator to try and identify the skill that was used. And the discriminator is only given access to the current state, right? And you repeat. You get a new action, get a new state, and keep training your discriminator. And so, so that was my break reminder there. So, we're training the skill, so the reward is based on how well you can discriminate the state, right? Discriminate the skill. So how well we discriminate it becomes the reward. So we train our policy to become more discriminable over time. And we're also training our discriminator to better discriminate between the policies. Yeah. So let's look at the algorithm side here. So we sample skills, and we have some initial state. So then we sample an action, we take a step in the environment, and then we compute the probability of that Z given the state S. And so then our reward is based on this, so the better we're able to discriminate the correct skill, the more the reward. And the way they do that is they use a log. So basically a log will punish if you have a very small probability of the correct skill, then you'll get a big punishment. If you have the probability of that skill was almost 1, so you pretty much predicted it right, the log will be close to 0. So we punish poorly discriminating the correct skill. And so then we do our updates to maximize the reward, which was basically this. The probability of each skill, it's we do uniform sampling, so this probably is just going to be, this is going to be a constant, so we can ignore that. And then we'll update our discriminator to better discriminate the skills. Cool. And so the discriminator, if it's kind of up to date, it roughly approximates how, like, the actual probability that it is that skill, right? If it's fully trained, it gives you the actual probability that it is that skill, given, you know, all the information that's available about the skills so far. All right. Cool. So, right. So for skills to be useful, we want the skill to dictate the states. So they give a great example here. If your robot is grasping a cup, right? It could grasp it with a lot of force or just enough force that it doesn't slip out of your hands, right? But both of those basically have the same state, and basically they're the same skill, grasping a cup, right? So that's why we use states, whether we can discriminate based on states as our kind of our metric of whether we have distinct skills. And discriminability is not enough because, you know, holding the cup here and holding the cup here, those might be discriminable, but they're not very distinct skills. So if we add some randomness in, then it would be very hard to distinguish one that's on average here and one that's on average a bit to the left, right? So by adding lots of randomness, we need to have very distinct types of states. So we have diverse skills that way. Cool. So that allows us, or it encourages us to kind of explore the possibility of all the range of all possible skills that produce distinct states. All right. Cool. And so what we will produce overall is, let's go back to the web page here. So these look all pretty useful, but some of the skills might, like one of the skills might just kind of do nothing, just like randomly jitter around. But then all the other skills will be distinct from that. And so you should only have one skill that's really just totally randomly dithering, right? So we can have one skill that's totally useless, but that means the other ones will be more interesting to be distinct from that first one. Cool. So let's look at the equations they use. So in the end, basically we just maximize this. So we maximize the entropy of the actions. If you have looked at maximum entropy, let me see, like maximum entropy Q-learning. I mean, this is already built into those methods, and they use soft actor critic, which is a math maximum entropy formulation. And then here, this is just the entropy of Z given, this should be given the state, sorry. So this is, and to estimate this, we use our discriminator. Can we discriminate the skill Z based on the state S, right? So our discriminator allows us to approximate this entropy. So this here is the formulas from the paper. So they say, so we start with this and then we work it into this formulation, and then we can ignore this part. All right, so we want to maximize the mutual information between S and Z. So the state is continuous, right? So we don't really want to work in terms of the entropy of continuous stuff, because entropy is kind of funny in the continuous realm. So let's work with the entropy of Z. So the mutual information would be then the total entropy of Z, so right, the total information there, minus the information of Z given your state S, right? So the difference between those would be, so given state S, we need less information, right? Because given the state S, we know it's more likely to be a certain skill, so then we need fewer bits to encode the skill, right? So then the difference between those, that's the mutual information, right? That's the information that S can provide about Z. Cool? And this term stays the same, and this term becomes this term. So this is basically, so everything's conditional on the state here. So we can just look at the mutual information of these two. Let me see. So Z, hold on a sec. Right. So thinking about it a bit more, I would just ignore this. I would just say, I mean, this makes more sense. We're going to maximize for each skill. We're going to maximize the entropy at each step, right? So yeah, given a state, we want to maximize the entropy of the action. Yeah, so for each skill, we're going to maximize the entropy of the actions at each step. And so here, this became that. They just hold the distribution of skills as uniform. So then we can ignore this term because it's constant, and we can just keep this term. So you see. Right, yeah, and so we want to minimize the entropy. Since we're maximizing this overall with a negative, we want to minimize the entropy of the skills given the state, which means that the state should basically be able to tell us the skill, right? Cool. All right, so I have a bit more detail here. We can break this mutual information into these two terms. And so I like to write it this way. So really we're taking the expectation, we're taking the expectation, that doesn't work. We're taking the expectation over all the skills of the for each skill, the entropy of the skill given. Sorry. Yeah, we're taking the expectation over all states of the entropy of the skills given that state. So this is just entropy over all states. That's basically given the data we collected. Yeah, Z is discrete, which is why it's easier to work with the entropy of Z rather than S. And we can estimate this by just creating this predictor, which we'll call Q phi, which maps from from SZ to 0, 1. So it's just giving us given the skill, for each Z, it's giving us the probability that it is that skill, Z, right? So this will give us a slight overestimate of this. Okay, it should give us approximately that, right? Because this should give us approximately the probability, and then we'll take the ln of it. Yeah, so we'll see this discriminator come in later. So how to optimize each term in this? Well, basically we can ignore the first term. This second term, so maximizing, sorry, this second term, basically we just use our discriminator. And so the entropy was the negative ln, so negative entropy will just be the ln of this discriminator that we train. And then for this term, maximizing the entropy given that you have a certain policy, Z, for that skill, this is taken care of by soft actor critic or any maximum entropy formulation, Q-learning type formulation. Cool. So they have an interesting comment about stability. So there's some methods where they'll use GANs, right? Generative adversarial networks. So when you have an adversarial formulation, you're training a discriminator and you're training something to try and fool the discriminator. So the discriminator is trying to like minimize something, and the thing that's trying to fool it is trying to maximize that same objective, right? And so you get the minimum along certain dimensions, say the minimum along certain dimensions and the maximum along other dimensions, which means that really you have a saddle point, right? And when you have this adversarial thing going on, I guess this is just less stable. I don't totally understand that, but it kind of makes sense that when you have two things working in opposite directions, that that might be a bit less stable. Whereas in Dyne, both of them are trying to maximize the same thing, right? The discriminator, improving the discriminator would improve the reward, and improving the reward directly through the policy also, that's improving the reward. So it's a cooperative game rather than an adversarial game, which apparently gives you more stability. Cool. All right, so we're going to go over some questions here. So these are an opportunity for you to pause the video and think about the question, and then watch the video and see my answer, which is not necessarily correct. This was just part of my learning process. Yeah, cool. So, does discriminating on just the single states, does that restrict you to learning skills that visit disjoint sets of states? And the answer is, of course, no, because RL algorithms can do things now in order to get rewards in the future, right? So even if it has to visit some of the same states at first, as long as it eventually gets to different states, then it will get reward, and it will get rewarded, and yeah, and so it will learn this, right? So they give the example, agents can learn to go down the same hallway so that once they get out of the hallway, they can see distinct things and therefore experience distinct states. All right, so how does Dyne yield diverse skills? This should just be review. And the answer is discriminability plus maximizing entropy in the actions for each skill, which pushes things apart to remain discriminable. All right, so let's interpret this. And so here's my answer. We went over this a bit earlier. Yeah, so I'll just carry on. So how would you optimize the terms in this? Again, we don't optimize that one. It's uniform, and this is the discriminator, the log, optimize the log of the discriminator, and maximum entry formulations. We'll optimize that. Okay, why is this approach relatively stable? Well, we just went over that. We just went over that. How might we use this to help solve RL problems where we do have explicitly provided rewards? Just think about that for a moment. So here's my answer. So a significant advantage of this is that we can learn useful skills without explicitly providing rewards, right? So it can be a lot cheaper to collect this data, right? Yeah. And so some of the diverse skills might already solve the problem. Like here, it learned to run forward, right? Just to increase the diversity of the skills learned. So we might basically already have solved our problem just by random chance, and even without having to do any reward formulation, like reward what is it called? Where we tune our reward to make the problem more solvable. Well, just by learning diversity, we can solve the problem without having to do any of that, and then maybe we can just give some final simple reward to fine-tune what we learned. All right, reward shaping. So it might help us reduce the need for reward shaping. Also, we have learned, once we learned a diversity of skills, these could become actions in a higher order reinforcement learning algorithm in a hierarchical reinforcement learning formulation. Now we could also combine, jointly provide rewards for provide the dyne rewards for discriminability and provide rewards for shaped rewards for the specific RL task. I notice that when I train my PPO agent on humanoid flag runner harder, it seems to get stuck in a local optimum. What I could see happening is with dyne is that one of my many agents that I'm training, one of the many skills, would get stuck in that local optimum, and that would push other skills away. And so those other skills would hopefully go on and find the global optimum. Yeah. And I imagine we could also combine this with some evolutionary type algorithms as well, where we knock off some skills and duplicate the skills that have been performing well on the explicitly provided rewards. Cool. So that's all. I hope this helps give you an overview of the paper. My recommendation would be to just go over these questions again. Probably just scroll the video back and go over them, think about them another time, and then maybe schedule tomorrow and then a few days later to go over this again if you want to really drive home your understanding. And of course, at some point I would also read the paper. Obviously, I have not covered everything in the paper, but hopefully this gives you a good high-level overview of the paper. Thanks for watching.